Okay, so in the last class we have discussed the zeolites. So the zeolites were crystalline materials that had micropores. So in this class we will start to learn about periodic mesoporous materials. And mesoporous materials are materials that have pore diameters between 2 and 50 nanometers. Materials that have larger pores than 50 nanometers are called macroporous materials. So zeolites have crystalline micropores, and they also have crystalline pore walls. Mesoporous materials can have disordered mesopores. They can also have amorphous pore walls. They can have periodic mesopores but amorphous pore walls. Some also have periodic mesopores and crystalline pore walls. So we'll here focus on so-called periodic mesoporous materials, in which the mesopores are periodic, but not necessarily the pore walls need to be crystalline. So the field of periodic mesoporous materials took off in the year 1992 with the discovery of the first periodic mesoporous silica. Its name is MCM41, whereby MCM stands for mobile composition of matter. And as the name says, this material has first been discovered at mobile oil. The 41 is just an experiment number. So how can you prepare such a periodic mesoporous silica material? You can prepare it simply from a silica precursor, such as tetraethoxysilane, in the presence of a cationic surfactant, such as cetyl trimethyl ammonium bromide, in a somewhat basic ammonium hydroxide solution near room temperature. So how can we understand the formation of a periodic mesoporous silica material? Well, in the first step, the tetraethoxysilane hydrolyzes, and we form silicic acid. Okay, and in basic solution, that silicic acid is partially deprotonated, and for that reason, there are Coulomb forces between the deprotonated silicic acid species and the cationic template. So what happens is that in a cooperative self-assembly process, we form micellar structures out of the cationic surfactant, which have a high concentration of silicic acid species in the periphery. Now you know that silicic acid is only stable at very low concentrations. And for that reason, we have preferential polycondensation of silicic acid around these micellar species. So that results then in layers of silica around the micellar species, and these species further aggregate together to form a periodic mesostructured surfactant silica composite. Okay, in which, in the case of MCM41, we have cylindrical micelles that are periodically ordered but are separated by silica pore walls. So in order to convert this composite material into a real porous material, you can remove the template by combustion, and then we have the MCM41 material with cylindrical mesopores. All right, so a significant extension of this chemistry was then the discovery that also non-ionic block copolymer templates can be used for the preparation of periodic mesoporous materials. The use of these non-ionic surfactants allows for much larger pore sizes of up to 60 nanometers, and the pore size can simply be tuned by varying the molecular weight of the polymer. So here you see two examples of two block copolyethers, which are typical templates. So these are tri-block copolymers. They have two hydrophilic ends. These hydrophilic ends are ethylene blocks, and you have a more hydrophobic propylene block in between. The propylene oxide block, not the polypropylene block, is more hydrophobic because of the methyl group. The methyl group is significantly more hydrophobic than CH2 groups, and you have only CH2 groups in the ethylene oxide block. Okay, here's another example. This is called P127. This is nothing else but a trade name given by the manufacturer BASF, in which we have 106 ethylene oxide blocks in the end units and 70 propylene oxide blocks is the hydrophobic middle part. So variation of the molecular weight of the polymer is one parameter that you can vary in order to tune the pore size, but it's not the only one. Another parameter is the addition of hydrophobic swelling agents. For instance, 1,3,5-trimethylbenzene can be used to increase the pore size further. Why does it increase the pore size further? That's because when we add such a molecule to the solution, due to its hydrophobicity, it will go into the hydrophobic core of the micelle, and thereby it will actually swell the hydrophobic core of the micelle. So that means that the micelle becomes even larger, and that in turn means that the resulting pore will have a larger diameter. So one significant difference between these Block Copolymer templated periodic mesopore silica and the ionic surfactant templated mesopore silica is that the pore walls of the mesopore silicas templated with a non-ionic surfactant are typically microporous, while those that are templated by a cationic surfactant are typically not microporous, they are dense. And that difference can be explained that in the case of the non-ionic surfactants, the polycondensing silica can actually to some extent penetrate the hydrophilic block of the polymer. Okay, so that after you remove that polymer by combustion, you're creating actually small micropores within the pore walls. Okay, so that's not the case in the case of the ionic surfactants. In this case, the silica actually does not penetrate the hydrophilic part of the micelle, just because the hydrophilic part of the micelle is just a very small ionic head group, such as a trimethyl ammonium head group. Another difference is that in the case of the non-ionic templated mesopore silicas, the template can only be fully removed by combustion and not by extraction. Okay, and the reason for that is, again, that the silica infiltrates the hydrophilic part of the micelle, okay, and that traps some of the hydrophilic parts of the micelle within the silica pore walls. Okay, so therefore, by solvent extraction, you cannot remove the polymer fully from these silicas. Okay, whereas in the case of the mesopore silica, which are templated by ionic surfactants, you can fully remove the surfactant also by extraction, not necessarily you have to combust the template. Okay, so these periodic mesopore silicas that are templated by Block Copolymers are called or many of them are called SBA type silicas, named after Santa Barbara, University of California of Santa Barbara, where they have been discovered by Galen Stuckey and co-workers in the late 90s. All right, so now we cannot only have different pore sizes, we have also control of, sorry, about the pore types and the pore systems. So generally, we can distinguish between cylindrical mesopores and spherical mesopores, whereby the cylindrical mesopores can be either straight, in this case they are typically hexagonally arranged, making a honeycomb system, whereby either they are completely separated from each other by the channel walls, by the pore walls, or they can be interconnected via little micropores, as indicated here. And that's the case when you use a block copolymer as the template. All right. So the other possibility is that you have a so-called gyroid structure. In this case, you also have cylindrical mesopores, but these cylindrical mesopores, they form a three-dimensional channel system. And actually, they do not only form one channel system, but two channel systems that are actually interpenetrating. Okay, and the second channel system is independent from the first one, meaning that there's no direct connection between channel system 1 and channel system 2. So overall, this so-called gyro structure is cubic. Okay, you see here again the overall pore system of this gyroid structure. So the other possibility is that we have spherical mesopores, and these spherical mesopores, they can then be arranged in different ways. Okay, very common are closed packed structures of these spherical mesopores. So we know, for instance, mesopores that pack in a face-centered cubic closed packed structure, and mesopores that pack into a body-centered cubic closed packed structure. So again, the principles of close packing play a very important role here. So typically, these spherical mesopores are not fully separated from each other. Rather than that, they interpenetrate to some extent, and that interconnects these spherical mesopores via bottlenecks. Okay, and while the bottlenecks themselves can have several nanometers in pore sizes. So that leads to overall three-dimensional pore systems. Okay, then now let's look more closely at the question, what determines the type of pore that forms? This is overall a complex question, so there are many parameters that can influence the pore system, such as the temperature, the pH, the concentration of the surfactant, as well as the concentration of the silica species. One important parameter, probably the most important parameter, is the so-called packing parameter, which is associated with the shape of the micelle, which is a result of the relative size of the hydrophilic component of the surfactant versus the hydrophobic component of the surfactant. And this is given by the so-called packing parameter. And you see here the definition of that packing parameter. It is the volume of the hydrocarbon core of the surfactant over the hydrocarbon chain length over the effective head group area, whereby the head group area is the hydrophilic part of the surfactant. So these three variables essentially determine the how conical the surfactant is. Okay, so when we have a packing parameter of smaller than 1/3, then that means that we have a large hydrophilic head group relative to a fairly small, relatively small hydrophobic tail. Okay, so when these surfactants form micelles, then because of the large hydrophilic head, we get a high curvature for these micelles, and therefore these micelles tend to form spherical micelles. Okay, so in turn, when we use such a surfactant as the template, we get spherical pore systems as the result. Okay, so when the packing parameter varies between approximately 1/3 and a half, then the hydrophilic head group is already smaller relative to the hydrophobic tail, and therefore the curvature of the micelles tends to become smaller, and under those conditions we typically form cylindrical micelles, and then these cylindrical micelles tend to assemble into hexagonal arrays when interacting with silicic acid. So when we increase the packing parameter even further, between about 1/2 and 1, then we have almost cylindrical, a cylindrical shape already, so the curvature becomes even smaller. And a result of that, we can form flexible bilayers and vesicles. And at packing parameter of 1, we then can expect planar bilayers because there's no reason or driving force for a curvature anymore. So the hydrophilic part and the hydrophobic part approximately consumes the same space. Okay, so in this case we can form so-called lamellar structures. So we have layers of silica and planar bilayers of surfactants, and these layers alternate. So this is so-called layered, also called lamellar mesostructure. So if you increase the packing parameter even further to larger than 1, then the hydrophobic part consumes more space than the hydrophilic part. So therefore the curvature is inverse. The hydrophilic part now points to the inside and the hydrophobic part tends to the outside, and you cause a structure like this an inverted micelle. Okay. All right. So periodic mesoporous silica materials can be prepared in various morphologies. So in the prep that I previously described, you get your periodic mesoporous silica as a powder, which just drops out of solution. But you can also prepare periodic mesoporous silicas as films, as well as monolithic blocks. So when you want to make a film, you can use a technique which is called evaporation-induced self-assembly, which is a form of two liquid crystal templating. So in this case, you can actually prepare a solution of your silica precursor, such as tetraethoxysilane, in ionic surfactant, for example. In non-ionic surfactant would also work in the presence of weak acid and ethanol. Okay, and then you can actually stir that until the tetraethoxysilane has sufficiently hydrolyzed to form more polar species that are miscible with this more polar aqueous solution. Okay, so the tetraethoxysilane itself is actually very little polar and is not miscible in the aqueous solution. So once you have a clear solution, you can just drop that clear solution onto a spinning substrate, for instance, a spinning glass slide. And what happens then is that the liquid actually radially spreads out from the inside to the outside. And there's, of course, a high surface area for that liquid. And for that reason, the solvent can quickly evaporate. So the ethanol component will evaporate actually quite quickly, and that will lead to an increase of the concentration of the silicic acid, which will now start to polycondense. In a cooperative process, it will again polycondense around the surfactant templates to form a film on your substrate. In that film is typically in the order of a few 100 nanometers thick, okay, depending on the amount of liquid you deposit and also depending on the spinning rate. You see here actually scanning electron microscopy images of the respective firms. So this part here is actually the substrate. Sorry. And this part here is the periodic mesoporous silica film above the substrate. And you see that this film is actually less than 1 micrometer thick. And within the film, you have periodic mesopores. And when you have hexagonal mesopores, then these mesopores typically lay actually flat on the surface. They typically do not stand perpendicular to the surface. Okay, so this evaporation-induced self-assembly is a form of liquid crystal templating, because we form a true liquid crystal, and the true liquid crystal forms because of the evaporation of the ethanol, which increases the concentration of the species so that actually liquid crystal of the surfactant forms, around which the silicic acid then polycondenses. So you can expand this prep to the preparation of truly monolithic blocks of periodic mesoporous silica materials. And you see such a photograph of such a material here. Okay, so you see that it's a glass-like block, but it is mesostructured in the sense that you have, well, micellar structures that are surrounded by silica material. So here is how typical prep works. So this prep requires a very high solubility of the templating agent. That is because we need to form an actual liquid crystal. So therefore, the ionic surfactants are actually not so suitable in order to prepare monolith, but the block copolymers are, because they have a very high solubility in water. All right, so for instance, you can use P123 as a template, and you can again first prepare your silica soil. Okay, you can start out with tetramethoxysilane, for example, hydrolyze it in water and hydrochloric acid to form silicic acid and methanol in the presence of that template, okay, whereby the concentration of the template is now so high in that vessel so that it forms actually a liquid crystal. All right, now that silicic acid has no other chance but actually polycondensing in the voids between the liquid crystal. Okay, so the polycondensation leads to the fact that your silica soil transforms into a silica gel. Okay, then this silica gel can be further aged, okay, in order to complete the condensation process. And in order to avoid water to evaporate, you can actually put a liquid paraffin layer on top of that silica gel and then age it at a temperature of 60 to 90 degrees. Okay, and that actually avoids the evaporation of water, and that actually avoids cracks in the monolith to form. And at the end of the process, you get a monolith as shown here. Okay, so this monolith still has the polymer in it. So you still have to remove the polymer, and that's a challenge in itself, to remove the polymer without cracking. Okay, so when you actually just use the traditional template removal process, calcination, and heat that material to about 3 to 400 degrees Celsius to decompose the organic component, your monolith will crack. Okay, so this doesn't mean that your mesopores actually go away, but you have actually macroscopic cracks just because of the mechanical stress induced due to the temporary removal process, and also in part due to further condensation of the framework. Okay, so you do not have fully polycondensed the framework typically before you remove the template, so there are also always silanol groups left, and these silanol groups can then further condense upon calcination to form silicon oxygen silicon groups. All right, now we can also give these periodic mesopore silicas more functionality by using the surface, the pore surface chemistry. As I mentioned before, the mesopore silicas often have, or mostly have, cyanide groups on the surface. They actually do not have crystalline channel walls. Also, I should mention that. So that's a difference to the zeolites. And you can use the dangling cyanide groups that hang into the pores in order to give these pores more chemical functionality. Okay, so you can react them, for instance, with chlororganosilanes. Okay, and then the chlorosilane functionality reacts with the OH groups to form silicon oxygen silicon bridges, and the organic functionalities hang inside of the channels. Okay, so this way you can both tune so this way you can tune both active and passive properties of these pores. So a passive property would be, for instance, the hydrophilicity. So these pores would certainly still be hydrophilic, while after the functionalization they would be hydrophobic in case this group R here is a methyl group, for instance. But if that R group is a more active group, like a catalytically active group, for instance, you can also render these periodic mesoporous materials with active chemical reactivity, such as catalytic activity. Okay, another way to functionalize mesoporous silica with organic groups is to polycondense purely inorganic precursors, such as tetraethoxysilane, with organo triethoxysilanes. So in this case, you substitute one ethoxy group by a terminal group R, whereby this group R is bonded to the silicon via a silicon carbon bond. And then you can do just the same cooperative self-assembly process, but with the difference that now you have two components that, well, co-polycondense. Okay. This method has the disadvantage that these terminal organic groups, they actually stabilize the framework. So you can only go up to a ratio of 25% organosilane relative to the inorganic precursor. If you go higher than that, then you get disordered pore structures, or the pore structure even completely collapses. However, you can go around this by not using a terminal organic group, but a bridging organic group that bridges two silicon tetrahedral centers. So in this case, the organic group has a bridging function, and for that reason it stabilizes the pore walls, and for that reason you can use such a precursor as a single source precursor, and that then boosts the number of organic groups that you can incorporate into such a structure. So in a fully condensed framework, you have then a ratio of oxygen to the organic group of 1.5 to 0.5. These organic groups can have a variety of compositions. So you can use simple methylene groups, ethylene groups, or ethylene groups. Also aromatic bridging units, such as thiophene, benzene, or ferrozene works well. But you have a limitation with respect to the flexibility these groups can have. So for instance, when you use propyl groups or other alkyl groups longer than propyl groups, the self-assembly process doesn't work anymore. Okay, so a certain level of rigidity is required in order to maintain the porous structure. When you use aromatic groups, you can even induce partial crystallinity into the pore wall structure. You see that actually here. So you see here periodic mesoporous organosilica with biphenyl groups, and you see that these biphenyl groups are rigid and can actually interact with each other through hydrophobic interactions. So they form layers within the channel walls that are organic, and then these layers are separated by more polar silica layers. So this is a means how you can introduce a certain degree of order into the pore walls. You use aromatic groups that can then align within the channel walls. All right. Last but not least, let me briefly talk about how you can increase the organic content even further when you actually use a ring structure, such as this one. Then you see that you have actually not only one organic group attached to the to a silicon, but each silicon is actually attached to two bridging groups. And that increases the ratio between the organic group and silicon further to a ratio of 1:1. So you can have twice as many organic groups within the channel walls. Also, such a ring structure easily assembles to form a periodic mesoporous organosilica material. All right, then let us just stop at this time